us again. This is the 12th Hackaday quantum computing class, and also for a new round that we started 3 weeks ago. For people who joining from other communities, that's session number 4. I want to first congratulate Hackaday for launching the Hackaday U. This is an alternative grad school for hardware hackers. We're very excited that during this time where people staying at home, we have all these really interesting topics that's offered by Hackaday, and the quantum computing class is one of the first classes that we started. So welcome to this new interesting way of studying. And I hope that for anyone who's just joining because of Hackaday U, you can also enjoy quantum computing class. We have started this quite some time ago. If you miss any of the previous classes, the Hackaday project Introduction to Quantum Computing is where you can find all of the past recording and slides. So you can search on Hackaday, or someone can post a link here. Hey, Megan, I'm actually gonna make you the co-presenter, so Megan can also monitor over here. Cool. The class is every Sunday. We talk about 30 minutes, and sometimes it goes a little over. We also started doing coding exercises in the class, and we have some time for Q&A as well at the end. The documents that we use are from the Microsoft Q# documentation, and the coding exercises are from the quantum katas. For people who haven't seen this before, you're gonna see this live. We're gonna do some coding exercise together. Now we, in the previous classes, had discussed superposition and interference, which are two of the most important concepts you need to know for quantum computing. Today we are going to discuss entanglement, and note that both interference and entanglement are results of superposition, which is the fundamental nature of a quantum state. We always go back to this picture to think about how superposition works. This, for people who have already seen this will be a revision for you. For new people, if this is a little too much, you can always go back to earlier classes. But this one is trying to show you when you have a qubit, you can represent it with addition of two states, 0 and 1. And they are in superposition, each having an amplitude in front of them, denoting how much of these 0 and 1 is in the overall state. Their amplitude squared would sum to 1 because their amplitude squared are the probabilities of having 0 and 1. When you have 2 qubits, you will have 4 different configurations in the overall state. And if you have 3 qubits, you have 8 different ways to combine each individual qubits. So then you know that when you have n qubits, it will have 2 to the n possible configurations. And what this tells us, so previously we learned about the amplitude and how they can interfere each other. And this time we're going to look at this other property, entanglement, that's also derived from superposition. Because you can have superposition, you can have different combinations of states to be in the linear combination. You can put some states in superposition, for example, this one. You could have 2 qubits, and they could be both 0 or both 1. And if you compare the first qubit in both options, they are different. And if you compare the second qubit in these 2 options, they're also different. And the other state you could do is to have 0, 1 and 1, 0 in superposition. You compare the first options for the first qubit, they are different, and the second qubit, these two options also are different. So these are actually some special states where you basically are eliminating some options. You can, for example, the first option is when B and C are 0, so you have 0, 0 and 1, 1 in your system. The second option is when you just have 0, 1 and 1, 0, so you eliminate the 0, 0 and 1, 1 states. When you put them into such linear combination, these two states are both entangled states, meaning that the qubits, the first qubit and the second qubit, are in entanglement. And what does that really mean? Is the correlation, the results of the qubits are correlated. For example, for simplicity, we just put equal amplitude. And this is actually a set of special states called the Bell states. These 4 states, and plus minus are just the 2 options with different signs. So in total, you have 4 states. When you have the same amplitude for these 2 options, you can have the Bell states. Take one of the Bell states as an example, say a 5 plus. If you measure the first qubit and you get your outcome to be 0, then you would know that it is from this state that your measurement result is being contributed from. You know that you don't even have to measure your second qubit. You already know your second qubit will be 0. So if your first qubit is 0, you will get this outcome with a probability of 1/2. If your first qubit, when you do a measurement, turn out to be 1, then you would know is from this state. So this one would not be contributing. You don't even have to measure your second qubit. You will know that it will be the 1, 1 state with probability of 1/2. So this shows us that the results of the qubits are correlated. This is what entanglement is. You can equally just do a measurement of the second qubit, and you will find you don't even have to measure the first qubit. You already know what your first qubit would be. So this is what this cartoon is trying to show, that if you know that your 2 qubits are entangled, you just need to measure one of them. You don't even have to measure the other one. This is what entanglement is about. And mathematically, you can also prove that is the case. We learned from the first session that you could, when you have 2 qubits, you can write them as a tensor product of 2 separate qubits if they were separate. So if you start with the entangled state, like a Bell state, and you have this vector, if you want to write them as a tensor product of 2 separate qubits, you would then equal this to this here. But then when you do the math, you calculate each element, what they would be, and see these 4 equations, you wouldn't be able to derive any result. So this set of equations would not have any solution, which means that you cannot describe this whole vector using 2 separate qubits. That's mathematically how you can prove something is in entanglement, is that if they were not entangled, you would be able to describe them as separate qubits. But if they are, you wouldn't be able to. You won't be able to find the solution. There are a lot of misconceptions about entanglement. If you read any popular science article or like some media coverage, sometimes people would say quantum states are weird. If you have entangled qubits. If you change one, the other one will instantaneously change no matter how far away they're from each other. And that's really a wrong statement, because entanglement is not about instantaneously transferring change from one qubit to another. Like this, I try to debunk this misconception here. When you have two entangled qubits, if you manipulate one of them, the other one doesn't get manipulated. The other one doesn't really feel anything. We know from previous couple of slides is entanglement is when you are measuring one of them. You don't even have to measure the other one. You would know what the outcome of the other one is because of this configuration they are being put in. And it's not a function of distance. So of course, when you separate them to infinitely far away, you're not changing anything. So this entanglement effect stays entangled. So there are a lot of misconception in the media about entanglement and how spooky and strange quantum entanglement is, but it's nothing but just putting your qubits in the special arrangement, and when you do measurement of one, you will know the outcome of the other. There are a lot of other commonly made mistakes. Here's a link. If you're interested, you should take a look at what's being really wrongly taught in quantum computing. And what that wrong statement will also violate is the law of nature. This slide we saw from last class about the different types of waves. But here I'm trying to reuse it for showing you that we talked about speed of light being a universal constant. And also we know that nothing travels faster than speed of light. If you had two entangled qubits and you change one and the other one will instantaneously change, that would imply that you're transferring information faster than speed of light, and that is not allowed. So that's why that statement is wrong. Now we are talking about multiple qubits, and we only learned the gates in the previous classes that are applying to single qubit. And we know that for single qubits, we have some commonly used gates like X, Y, Z, or Hadamard, or some phase gates. Those matrices are the gates that are applied to a single qubit, and knowing that a single qubit is a 2x1 vector, and you just use a 2x2 matrix to change them. But when you have multiple qubits, you can also use matrices to apply to them. And we're going to talk about how that's done next. And these we haven't talked about for people who were in previous several classes, they have seen this, but for the new set of classes, we haven't talked about these symbols yet. And these are called the circuit gates and components using a circuit representation. I'm going to show you how that works. So here is one of the most commonly used multi-qubit gates, actually 2-qubit gate, is the C-NOT. It's called a control NOT gate. For people who are familiar with the classical NOT gate, it's basically a flip between 0 and 1. So I think in classical, there's also a control NOT gate. So basically what it's saying is if you have a control qubit, the control qubit would determine what happens to the target qubit, which is your second qubit. It's reflected by this matrix here. You see the first quadrant here is an identity matrix, so nothing changes. But then the last quadrant is a switch. So if your control qubit is a 0, then nothing happens to the target qubit. But if your control qubit is a 1, your target qubit would either change from 0 to 1 or change from 1 to 0. Here is the outcome. Definitely try this at home. You can see that when your first qubit, which is a control, is 0, your second qubit is intact. but then it flips when your first qubit is 1. So use this matrix and apply it to your 4x1 vector, which is 2 qubits, and try to prove this yourself. Well, I'm here actually writing this proof for you for the 1-0 case. So go back and do this. For people who don't remember how to do matrix multiplication, this is how it works. Just apply the elements to your vector 1x1 cross and plus. And we used a block sphere to describe qubits graphically, kind of a easier way to visualize what happens to your qubit. But then we know that is only useful for single qubits. When you have multiple qubits, the block sphere is not useful anymore because block sphere is in 3-dimensional space, but when we have multiple qubits, it's multi-dimension. We cannot represent, it doesn't really help us since humans can only see up to 3 dimensions, but we can still use a graphical way to represent multiple qubits, which is using these lines. I like to make this analogy like music notes, which are these lines that tells you that it evolves with time. And now here, instead of having the music notes, we can connect different qubits. So each line is a qubit, but then we can connect them through some gates and lines. For CNOT gate, the dot is denoting which qubit is your control, and this circle cross is a target. And if you also just, when you try the math, you realize that this circle knot is exactly X gate, is a flip. So this circuit here shows a target B is controlled by your the first qubit A. So this is the input, this is the output after the CNOT gate. So there are also more commonly used gates, and a lot of them use controls, control Z, and this is a control CNOT. So they're all multiple dimensional matrices. So you can go and try to see this mathematically how it works. But we're gonna delve a bit deeper with control knot. And why are we talking about control knot here? Because that's how you can create a entanglement in your qubit system. And it's using everything that we've learned so far. Here, the I want to turn on the pen so that we can do the math together. Here, this simple qubit is, this simple circuit is exactly producing a Bell state. Just using a Hadamard and a CNOT, you get that. This is the table of input and output. So we should try doing an exercise. I'm gonna draw this with my mouse here. So say you first start with, let's pick one of them just to make it more interesting. Let's make the first qubit 1. So what happens when you apply this H gate to your first qubit? So nothing happens to the second one. You can just write that result. We know that when we apply Hadamard to either 0 or 1, it puts it in a superposition state. So when 1 has a Hadamard applied to it, you get the minus sign here. So you can write this out step by step with matrices, but because we already know what the result is, we don't even have to derive and write out the matrix. But for people who are super curious and rigorous, you can also prove this by writing out the matrices. Oops, this is wrong sign. it should be the tensor product. But it really is just showing that you can write your system like now your first qubit becomes a superposition and your second qubit stays the same. Then when you apply a CNOT, apologize for this ugly writing with my mouse. Now what happens then is you just keep writing based on your control qubit. Now your control qubit, if it is 0, then nothing happens. So you just copy that. Minus sign doesn't change. But now if your control qubit is 1, you know your second qubit will becomes 1. That's how you derive this table. So go back home and try proving the other ones. You will see with these 4 different inputs, using a Hadamard and a CNOT, you would get these 4 different Bell states. That's quite neat, and we can actually use entanglement in some simple algorithms. This is a superdense coding algorithm. Let's look at the story here. We are writing with representing everything using the circuit here. It's so simple so that we can just write out what gates are needed to each qubit. So you start with this H0, H Hadamard gate and C0. And we know, we just saw that this is trying to entangle these 2 qubits. So Alice and Bob prepare their qubits into an entangled pair. Say they start, so say this is the Bell state that they put their qubits into. Then they can separate themselves infinitely far away, it doesn't matter. Now Alice wants to tell Bob some classical information. She wants him to have a string of 2 classical bits, so 00, 01, 10, or 11. But she has a qubit in her hands. How does she do that? She can encode these information into her own qubit. And she's got different options. If she just want to send 00, she doesn't have to do anything to her qubit. But if she wants to change, send, say, the first bit to be 1, then she applies a Z gate to the first, to her qubit. If she wants to have the second bit to be 1, she would apply an X gate to her qubit. Now she only has 1 qubit. She can apply either or and both gates to her only 1 qubit, depending on what 2 classical bits she wants Bob to get out. So she does some encoding here. Now she can send her 1 qubit to Bob. Bob has 2 qubits, and we know that they're still entangled, and he would have these 4 Bell states with him. So if he then disentangle them, and that's just doing a reverse of a C0 and a H gate, he would then separate the 2 qubits. If he measures his 2 qubits, he will get either 00, 01, 10, or 11, based on what Alice did to her only qubit. Because we know they're still entangled, Bob would have one of the 4 options. After he disentangled them, and then measure them, that's the decoding step. He will get what Alice intended to send him. So what's better than doing some coding exercise? We're gonna go to the quantum katas. This is a reminder to show people what does Z gate does and what X gate does. So Z is giving you this minus sign here, and X is a flip. So these minus signs are from the Z gate. So let's practice this in the quantum katas. get out of the presentation mode. And then let's all go to the Microsoft. You can just search quantum katas. Should be the first one that comes up. We're gonna go to the Superdense coding exercise. We're gonna use the Jupyter Notebook option because we don't have to download anything. It just opens up the browser. If you've already downloaded the Quantum Development Kit, you can run this locally. Just waiting for Binder to load. Here is the link. Read this yourself, some Wikipedia pages and more articles for you to understand Superdense coding. We just gotta go ahead and run the packages. This is helping us set up the circuit exactly step by step. We can go back to this picture here. So if it's too small for you guys, you can do Control Plus on Windows or whatever equivalent on other operating system. You can enlarge the view on Teams. So this first step is that we start with 2 qubits, both in the initial 0 states. It wants us to prepare a Bell state. So we know that from this table here, we just saw, if your initial 0, is your initial state, then you just have to do the circuit to get it into this Bell state. If you want to prepare other Bell states, you can just do the flip for either your first or second qubit to put them into the other states. But here it just asks us to do the easiest step. So it's nothing but writing out exactly what you want your qubits to be. In a hard mod and a CNOT should give you the corresponding result. Oh, why is it complaining? Oh, because, yes, I wasn't thinking. You are doing the hard mod to your first qubit, and you have your Q1 as your control and Q2 as your target. This should do success. Now, the encoding part. So Alice has this classical message that she wants to encode is a Boolean bit 1 and bit 2. Now, this first line is actually a just reminding us how they should be. So it's a hint. We can just do this step here. Depending on which bit you want, so if it's 0, you do nothing. But if you want to have a 1, then you need to apply a gate somehow. So if your first bit, you want it to be a 1, then you apply the Z gate to that. And this time it's called QAlice. Now, you just do the same thing for other one, copying pretty much. If you want your second bit to be 1, what you do, you apply an X. So we are able to do this, sending information through this circuit because we already know the truth table for this algorithm. We know what result we get to knowing that we have put our qubits in a entanglement state and we know which entanglement state it is. If your starting point is a different Bell state, you can try it again and you can see what happens. So this is the encode message part. The third step is decoding. So it's now both Alice's qubit and Bob's qubit, but Bob does all the jobs after this. So you could write exactly this part using a C0 first, and Alice's qubit is the control. And then do a H to Alice's qubit. However, there's something, this will be correct, but there's actually something else you could write that is kind of a smart trick. There is something called the adjoint. And what is adjoint is this name that we, the operation that we give to a matrix that's unitary. So we have been talking about gates, and I mentioned that gates are reversible, that gates are, you should be able to apply gates to your qubits and do another set of the gates or original gates that can reverse your qubits back to where you started. And that makes sense, is that you shouldn't lose your quantum states when you have a quantum system. You can apply gates and change them, but then change them back. And mathematically, what is to achieve reversible is to have these unitary matrices. And how it works is, being unitary, it means when you do a transpose and then a complex conjugate, it would be the inverse of your original matrix. So this is for people who are more interested in the maths behind it. If this lost you, don't worry about it. But we do in Q# a operation that we call adjoint, which tells us to do the reverse of whatever operation you set up earlier. So in this case, you can equivalently write it as an adjoint of the first step that you set up, create entangled pair. Of course, you need to define your qubits. So that should do exactly the same thing as these two steps, because this one is doing an H and a C0. Doing an adjoint means do a C0 and H. So that's something new about Q# that I'm showing you today. And then you want to return your results. And we just did this protocol message. So here you would do protocol message. Now, a new operation here. And you see why I'm doing this particular katas is to show you all these different new things. This is a measure, then reset with the basis, the z-axis as the basis. So you could write, you don't have to write this in one single line. You could write, do a measurement, so do measurements to both of your qubits, and then you can reset. Why are we doing a reset is because we want to reuse this, we want to establish this whole algorithm, we want to reuse it. So we are doing a reset because later on in task 4 is actually asking you to put everything together in one operation. So here, that's why we're resetting it. And where do you find information about M reset Z? is on our documentation page. I'm showing you how you can find it. I have pasted the link. You can look at them later. There are two places you can find them and read about them. One is in the Microsoft documentation for quantum computing. In this API reference, you'll find all kinds of libraries about different gates. And then there is an M reset, is using the Z as your basis. And when you do a reset, it will reset it back to the 0 for your this block sphere here. So this is using Z as your basis. So when you do a reset, it will be this point, which we know is our 0 in this case. So just a little bit of nuance about the language itself. The other place you can find it is on the MS Learn module. I don't know how many people have taken the class I have been recommending. So go to the quantum computing MS Learn module. I have this link here. You can use later. And then do this, create your first Q-sharp program using QDK. Take a look at these exercise, and on this page, you will learn a bit more about the Q-sharp language and how these different operations work and the libraries and everything. So it also talks about reset. So here are the two places you can learn more about this. So I haven't finished this. We need to reset the other qubit. And this equal to 1 we have learned from last class. In this Boolean example, we let it to equal to 1, we'll get 1 as truth and 0 as false. So that's why we put them to return in this manner. If you want to know a bit more about this, take a look at last class where we did the measurement when we did exercises and learn about how measurement works. Okay, so this, okay, I know this would not work. Why? Because we actually need to open. That's why this is important here. Look at where this mreset Z sits. Is in the Microsoft Quantum Measurement library. So we actually need to open this here. Measurement. Otherwise, it wouldn't know the commands for measurements. Okay, there's still something wrong. Did I misspell anything? Message. Oh, of course I did. Wait. Ah, yeah. Hard to see. So that should be it. That should be how you can set up all of these steps. The last exercise, I'm going to leave it to you, is using all of these 3 steps. So you are using these operations that we set up in the last exercise, so putting everything together. So then you will have a full algorithm that you can just, next time, if you want to do a superdense coding, you can just use superdense coding protocol. You don't have to do any of these that are already written. That's it. That's for the superdense coding. Why is it called superdense? Because here we are sending 1 qubit, but in fact, it encoded in the whole system. It has, you're effectively sending 2 classical bits. So that's a nice little algorithm to show the usefulness of entanglement and entanglement only in this algorithm. We have a couple more algorithms that we're going to do next. Teleportation, CHSH game, they're all demonstrating entanglement. But the more fun algorithm and more useful ones are using both entanglement and interference. So we're going to do those a little later. So in the next couple classes, we will do some exercise of the other entanglement demonstrations. For anyone who complete any quantum kata, you should take a photo and screenshot, and I'm giving people this certificate that they can print on anything. So you can follow these tweets, these handles, tweet at them with your screenshots or use LinkedIn. So I know you have finished katas, so you get rewarded with the printable vector graphics. So nice to see people have already done that. Also, I'm giving this certificate to anyone who participates in the coding contest. It's happening right now. So register and do the exercises. Maybe you can win some award in the next day or so. We also have this Azure Quantum Developer Workshop. Azure Quantum is our cloud service. So everything that we learn in Q# using the quantum development kits, they can be used to run quantum program on the cloud. Azure is Microsoft Cloud. You can access real hardware through the cloud service. We're doing a developer workshop that is mid-July. Register now and to learn more about how you can use the Azure Quantum Service and how you can develop yourself as a quantum programmer. That is it for questions. You can ask them in the chat now. You can also post them in the Hackaday project page. Also, the recordings are on Hackaday projects and also YouTube. That's it. Let me take a look at the chat if there's any question. Oh yeah, you should ask me why it's called Superdense. Okay, semicolon, yes, thanks. I didn't see the chat when I was writing the code. For the instant message. So Meet asked, with regards to Bell's pair with two quantumly entangled photons, then at the moment of wave function collapse of one member by classical measurement, the wave function of other member is also collapsed instantaneously. So I have been avoiding to use collapse because as we learned last class, the interference is how we can describe what really happens in your quantum system. When you do a measurement, you're getting the result of a constructive interference. So the collapse is an easy way out about what happens during the measurement and people still use the term, but I don't think it's a good term to use anymore. And I can see why you're saying that the second one will collapse instantaneously, but we have done nothing to it. If we're not doing the measurement, even though we know what the outcome would be, but we are not doing anything to the qubit. So I think you understand it and I understand it, but the language here is what I'm trying to avoid using, which is misleading. So no information is traveled, that's correct. Hence no violation of causality. Copenhagen interpretation is what physicists came up with when they didn't know how to interpret measurement, and they're using the term collapse or project, or there are some other terms that, but there's not really, we know now that it's all about interference. Is this what is preferred by Microsoft Q#? So yeah, people are still using this term, but physically in Q#, we are just using a programming language to capture the gates and qubits. So sometimes people do use the term collapse, but as I mentioned, it's an easy way out. It's like just trying to say the measurement without explaining the interference. So, and by the way, these teleportation, superdense coding are kind of like toy algorithms that people can use to prove when they do a physical experiment, they can use these to prove that they do have entanglements and they do have quantum systems. So sometimes this teleportation algorithm is called the hello world of quantum. And when you can teleport your state, that proves that you have a quantum system. Why can't I spot these kind of mistakes when I make them? Why can't I spot these kind of mistakes when I make them? Oh, yeah, I think Adam is referring to the writing, the coding misspells. Roberto also asked why it's called Superdense. Coding contest. Yep. Thank you for the link. How do you mitigate decoherence errors? Yeah, so I haven't mentioned in this class about decoherence. In the previous class I did, not the previous, but the several classes before, when we first talk about entanglement and decoherence. So you have to build in your hardware error correction. You have to both in the coding level, hard-coded coding level, and the hardware level, you have to build different kinds of error correction. I'm not an expert in error correction, but there are many ways, and oftentimes you would hear people say functional qubits and actual qubits that's not used for the actual quantum computing, but they're used for error corrections. So we have to build multiple, more than what we need for the computation, actual qubits to counter the errors that we may measure. So that is, yeah, I think it's a little hand-wavy way to say how do you mitigate decoherence, but in the experimental level, that is, you have to counter the errors that could be introduced. The decoherence can happen whenever you have something other than your intended physical system that can come in. If, for example, your measurement probe, when it comes in, it could at the atomic level, it is also quantum states, and it can entangle with your qubits, and then it messes up your whole setup, your whole quantum system, and gets decoherence. Roberto says, seems to work for 1 qubit or small number of qubits. In a real system, you will have many qubits. Yeah. Would this work the same, or they would need modifications? I'm thinking like going from quantum to statistical mechanics. So there are a couple of things. This is, if you're asking specifically about superdense coding, then this is just showing a 2 qubit, but you can have many qubits to do superdense coding using similar logic. You just have to build it in your algorithm, and you need to entangle multiple qubits. If it's broader, not just about this algorithm, but other how do we modify? So the decoherence is what we need to account for. We have to build in the hardware architecture additional qubits to counteract this entanglement or error that's introduced in the measurement. But if you're just looking at the pure algorithm level, you can just, for small number of qubits, write very simple circuits to lay out what happens to each qubit. And when you scale to large number of qubits, you can use, that's why we invented this language Q#, because we cannot always be writing qubit one by one. So in theory, in a clean system, it works exactly the same. And we already know from last class that in nature, we have real quantum system has many, many kinds of wave functions in superposition, but we are just picking two of them to represent 0 and 1. So already having a computer that uses only 0 and 1 is a simplification of real quantum systems. So when you construct that in hardware, you have to make sure that you know which configuration corresponds to which state, and you're strictly putting them as your 0 and 1s. And the language is a pure thing that you can code each individual qubit with your kind of a theoretical level, but your question really goes into how the hardware needs to account for all these problems. Okay. Yeah, thanks everyone. Sumit also commented, usually anything above 8 qubit currently enough for any number from 0 to 255. Yeah, so depending on what kind of algorithms you want to build and what problem you want to solve, will have different requirements of number of qubits. Okay, so yeah, this is our ongoing research. How many qubits is needed for what? So having a few hundred definitely helps. We can do something very useful with a few hundred number of qubits, but then I don't think there's we have to be more specific. We can't just say it can represent the entire universe. In what way, we have to explain. So yeah, thanks everyone. Thanks for the discussion and participation.
Hi, Kitty.
Next day. Hi.
Hi, Kitty. Could I ask a question?
Yeah, sure. I'm gonna turn off the recording now. Thank you, everyone.